Hi, hello everyone. Sorry, I'm known for breaking type systems, but apparently I break all this as well. But thankfully there's lunch after this. I'll try to keep my time short, so it'll only take a little 5 minutes of your time. But let me go on with the talk. So my name is Ross Tate. I am a consultant for the Kotlin language team. And last year I gave a presentation on a new algorithm that we'd been developing. And at the time, I had thought this was a type-inference algorithm. But shortly after my talk, I realized I had stumbled into something new and something better than type-inference, but in a way that was hard to understand the implications of for a while. So this year, I'm going to share some of these new insights we've developed and illustrate the impact they might have on the Kotlin language. But before I go into that, let me recap at least one key point from my talk last year, which is why I believe Kotlin type checking should be decidable. With decidable type checking, you get a more reliable programming experience, right? You can plan your software architectures and just know they're going to work without having to worry about pitfalls in the type checker. It becomes much easier to standardize the language because the type inference algorithm no longer has to be part of the standard that we have to all agree upon. And it makes the language itself more stable because certain aspects of the language, like overload resolution, are sensitive to how the type checker works, so having a decidable type checker will make those features stable across language compiler versions. And lastly, it's way easier for us to add features to a language when we have a solid algorithmic foundation to build these features upon. So, despite all these advantages to decidability, it's often overlooked as something that's incompatible with other important properties that we'd like to have, like type inference. So let me illustrate a classic type inference problem that most languages have, and how we figured out how to overcome this with this new algorithm. So suppose we're trying to define last or null. We get started by first initializing our loop variable. That's the last match we found. We say, hey, initially it's null because we haven't found any matches. And with a production algorithm that we and many languages have, what will happen at this point is immediately it will say, okay, the type of last match is nothing question mark. And that's a problem because later on we assign an element of the list to last match, and that gets rejected. And so we've incorrectly rejected this perfectly valid program due to over-precisely initializing the type of this new loop variable. And this problem becomes more and more problematic as we try to scale up the type system and as we, as developers, are scaling up the kind of paradigms we're building upon that type system. So the team and I have been working on this new research algorithm that works very differently from this algorithm. Instead of trying to figure out what the type of last match is, it says, okay, well, last match enables a lot of flows to my program. Let's check if those flows that it enables are all safe. So for example, here we have null flows in and element flows in to last match. And then we see that last match flows into T question mark. And if we look at these endpoints, we can tell, well, yeah, clearly these are all safe flows to the program. And so we can accept this program. And what's cool with this new algorithm is we can actually do this guaranteed in polynomial time, whereas the old algorithm was actually potentially exponential time. So we have this algorithm that is both more intelligent and, at least theoretically, more efficient than the existing production algorithm. But what is this algorithm in more detail? Last time I kind of hand-waved over this. This time I want to dig into how this algorithm works, so you all get insights both into what's happening behind the scenes, but also into this interesting property that this algorithm has that's the basis of this talk. So I'm going to start with a minimal reproducible example of the key challenges that come up when trying to type check a Kotlin-like language. In this little tiny example, I have a loop that gets with a loop variable that gets initialized and updated, just like what we saw in over-precise initialization. So that turns out to be actually a pretty key challenge. And then the second half I have is this interface foo. Now, you've probably not written an interface like this, right? It has this complicated bar signature that returns foo of t. But the point of this minimal reproducible example is that it compresses the kinds of challenges that do come up in real programs. For example, the Kotlin library has cancelable continuation, which has this resume method that itself is generic in addition to cancelable continuation being generic. And that's actually even harder to reason about than this interface. And this interface is already hard enough that it breaks every single algorithm I could find in industry and in academia. So if you can figure out how to do this interface, we've made a big step forward, and that's what we did with this new algorithm. So I'm going to walk through how this algorithm works and type checking this program. The first thing we're going to do is not new. We're going to say, OK, this loop has some unknown type. We're going to name that type temporarily with this type variable L. And I put this little circle over the L to indicate that it's a hole in my program that I need to fill. The second thing we need to deal with is this invocation of bar here. Right? Because if we just look at that one line of code, that bar could represent many things in our program. Right? There could be many other interfaces besides this one I've shown here that provide a signature for bar. And we don't know immediately which one to use. So this is where traditional approaches or existing algorithms have gone wrong. They either are over-aggressive with how to resolve this, and they end up restricting what loop variable can be and incorrectly rejecting this program, or they tend to be overly structural in how to resolve this, and it takes us down this infinite path that makes it so they don't terminate. So what we're going to do is say, hey, I just simply don't have the information I need to resolve this right now, and I'm not even going to bother. I'm just going to listen to the receiver's type, in this case L, and once the information comes along that I need, then I'll resolve this method. And this on-demand approach turns out to be that breakthrough we needed to get it so we can handle this program. So with that in mind, let's go into thinking about the types in this program and how they need to be related in order for this program to be valid. So the first thing I have is I have this foo any type, right? That's used for my init variable, and that init variable then flows into my loop variable. So for that flow to be valid, I need to know that foo any is a subtype of L, this unknown L we've introduced. And that constraint already triggers a really important thing because it adds a lower bound to L, and we're listening to L in order to resolve this method invocation. And in particular, it says, hey, at this point, I know that L has to be at most a foo, right? And that means that this bar invocation has to resolve using foo's bar signature. And so now that I've pinned that resolution down, I can stop listening to L, and I can move on to saying, OK, I have the signature I need. Let's check that this invocation site conforms with that signature. For that, the first thing I need to know is that the receiver loop here is a foo. I don't necessarily know what it's a foo of. I just need to know it's a foo of something. So what I'm going to introduce is another variable, a, that represents this unknown something at this point that L needs to be a foo of. And then using that a, I can type check the rest of this method invocation by saying, OK, well, the loop needs to be a valid argument to this, and so L needs to be a subtype of a. And similarly, the type returned from this bar needs to be assignable to loop, so foo of a needs to be a subtype of L. And at this point, I have taken all the relevant constraints from the program and captured them in this little cloud. And we can move on to thinking about those constraints and saying, hey, do these constraints make sense? Do they represent a safe program? And the way I'm going to do the second half is say, OK, well, in these constraints are contained a bunch of flows, essentially, in my program. Right? So for example, I have foo of any flows into L, and L is going to flow into foo of a. And for that combined flow to be safe, I need to know that because foo is contravariant, that a is a subtype of any. Right? So I've derived this new property of our types, our unknown types, that needs to hold for this program to be safe. And I can keep looking for these kinds of flows. For example, foo of a also flows into L, which also flows into foo of a. And so we get that a needs to be a subtype of foo of a, again, due to contravariance. We keep going through these flows, and there's a whole bunch of them, and I can use an indexing structure to make this whole process efficient. And at some point, I'll either run into an error. I'll find something that says, hey, for this program to be safe, it needs to be OK for integer to flow in string. In which case, I can say, well, that's not safe, and I can reject this program. Or I'll get to what happens here, where I find that any new constraint I could derive from these flows happens to already be in that constraint set. And once I've hit that point, I have what's called a consistent constraint set. And last year, what I had proven is that this algorithm we developed is guaranteed to always terminate and to always only reject programs that have one of these flows that are incompatible, or determine that the constraint set is consistent, which is why I was comfortable talking about it last year. But there was this question I hadn't really figured out last year that we're going to dig into this time, which is, what actually is L, right? I've never figured out what L is for this inference algorithm. And if you look through all the constraints, you can figure out that there is only one answer, and that answer is fua, 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 forever. And what type inference research has shown, that is actually a perfectly safe answer to use. But that same research covers these sort of small languages like this, but when I try to scale that kind of approach to Kotlin's many other features, I just found they weren't scaling. I was spending all of my time, not on the algorithm itself, but just figuring out how to scale up these complex type constructions. So I said, okay, if this L can have this really convoluted type, did I really need to know what that convoluted type was? And if I didn't really need to know that convoluted type, did L really even need to have a solution? Did this solution have to exist? And to answer that question, this sort of existential question I had started facing, I dug into or revisited why is it that we use types in type inference in general. So one application of types is software documentation, right? You and I use types to read our own code and read each other's code. And having types like foo, 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 foo forever doesn't help with that. So if we can get a system that doesn't rely on those types existing, if anything, that seems like it would help software documentation. But inference in general is useful, and that lets you remit types that are only there for the type checker and only have the types that are useful for you to be able to read your code. Which gets me to machine-checked conformance, right? The type checker, the software documentation in this case, is actually checked by the compiler to say, hey, you said it should do this, and it does do this. And so now having this algorithm that's complete, that's decidable, makes that all the better, right? Because we don't have to add these types just to help the type checker anymore. We also use types in interactive development, right? If you're typing your code, things are going well, you get pop-ups saying, hey, there's something you could do here, here's something you could do there. But it turns out all that pop-up information doesn't really need full inferred types, it just needs shallow information we can get from these constraints. So we can still serve that use case. In the other case, you start typing and then it says red flag, something's wrong here. And with this algorithm, what we can do is whenever there's this incompatibility, we can actually redraw a flow in your program that illustrates that incompatibility, which in many ways I think is an improvement upon this convoluted type is incompatible with other convoluted type. So I think we can actually improve upon it here as well. All right, lastly, types provide runtime guarantees, right? At least in Kotlin, right? We get memory safety from these types, and I want to still provide those safety guarantees. And this is where I ran into real hurdles because all the algorithms I know of approve safety by showing that these types exist, these solutions to these constraints, and that was exactly the step I wanted to get rid of. So what I did is I developed a whole new notion of what it means for a program to be valid, and I called this type consistency, and it captures this notion of, well, I've shown that all the flows in the program are consistent. And I showed its equivalence to that constraint set being consistent, which is what my algorithm decides. So I basically had built an algorithm that decides this type consistency property. And then I proved that type consistency, in fact, ensures memory safety in these runtime guarantees we're familiar with. And this proof actually turns out to be more direct than traditional type inference proofs. So I was able to mechanize all of this. So we actually have more confidence in these runtime guarantees than traditional type inference algorithms with this new approach. And so reviewing this list, we can see that we can achieve all these sort of purposes of type inference, but without actually doing type inference. And that put me into an awkward spot because what is this algorithm then if it's not a type inference algorithm, right? It's doing everything we use type inference for, but without actual type inference. And so I said, okay, well, what type inference does is it works by filling in the holes in your program. Whereas what this algorithm does is it works by factoring those holes out of the flows in the program. So as a pun, instead of calling this type inference, I call it type outference. And this talk really should be called Designing Kotlin with Type Outference, but I couldn't do that because nobody would know what I was talking about. Oops. So now that I've introduced this term and given you some context for why I had to introduce this term, let me move to the second half of this talk and illustrate the impact this can have on the Kotlin language design. Starting with a familiar example, which is unions and errors, which I also spoke about last year. So I'm going to, once again, recap some slides from last year to give us all this context. Union types have this nice thing where they're the type that contains the two types being unioned together. And there's a particularly important example in Kotlin, which is T question mark, which is also the same thing as T union null, right? Because it contains all the T values and it contains null. But many people have shown or have pointed out that unions have other uses besides null, and that asks for support for it in Kotlin. But there's this problem that unions have with efficient program validation or type checking. And to see why, try to infer what this whole X needs to be in order to make mutable list of X a subtype of mutable list int union mutable list string. Right? So you have these two cases, has to be one of these two cases. It's an invariant class. You'll find that this works when X is string or X is int. And that or there is really problematic because it makes the type checker sort of commit to a choice, and you can have a bunch of these choices that can cause an exponential search through your constraint system. And that can blow up our type checker. We don't want that for Kotlin. So we still had these applications of union types that people were pointing out, one of which was errors. So we started investigating this idea of categorized union types. And the idea here is that we're going to take our types and group them into categories. So one category is null, it just has the null value. Another category you're familiar with would be any, right? It has all the interfaces and classes that you're already familiar with. And then we're going to introduce new categories, one for each error, so that you could have these errors that we can union together. And then now we're going to say, okay, unions are only allowed when the two types being unioned together are in separate categories. And this gives us this nice property that says, okay, if I want to know whether T is a subtype of a union, I can say, what's the category of T? Okay, whichever case is in that same category, that's the only one I have to consider. I can avoid this branch, I just commit to that one case. Or at least, that's the lie I told you last year. So this year, we're going to dig into this interesting corner case that causes me lots of headaches, which is what happens if T itself spans multiple categories, right? T could be a union type. It turns out that case is actually really easy to solve. That's not the hard part. The hard part is T can be a type parameter that is upper bounded by a union type. These are the kinds of things I have to deal with in making these algorithms. So let's go into what goes on there, in particular, why that causes problems for inference. So this is the kind of function we'd like to be able to provide with this unions for errors extension to the language. Right, it gives you, say, okay, here's a result, branch on whether it's a value or an error, and call the appropriate function. I can type check this. This is fine. But things get more difficult when I try to use this generic function. So I'm going to give a little toy usage of this function, where I call handle, I take the result, and in either case, I return it. So this is just the identity program, but written in a way that's hard to type check, and in particular, hard to do type inference for, as I'll illustrate next. So now, let's think about how we have to how we can verify this program. The first challenge is that this handle, called a handle, right? Handle is a generic function, so I have to infer its type arguments. And so I'm going to introduce a hole for each of these arguments. So here's one type parameter, and say, okay, well, there's some unknown v that needs to be a subtype of any. And there's another type parameter, so there's some unknown e that needs a subtype of error. And then we also have an unknown k that initially, at least, is unconstrained. Then I say, okay, now I have these holes named and constrained. Let's look at what the actual arguments are and make sure they're all compatible. So result here needs to flow into this union type. And so that tells me that R needs to be a subtype of this union of these two unknown types. And notice that R there does not have a little hole over it. It's not a hole in the program I get to fill. It's a type parameter, and I have to make this work for any type parameter, or any type it could represent. And that will turn out to be a key challenge. But let's move on and check the rest of the arguments first. So next thing I do is I hand the identity function off to onValue. For that to work, I need to know that this unknown v is a subtype of the unknown k. And I hand off the other identity function to onError, and that means that e needs to be a subtype of k. And lastly, I take the result of handle and I return it from the identity function. So k needs to be a subtype of r. And at this point, I've captured all the constraints in the program that are relevant and put them into this little cloud. And we can move on to just reasoning about those constraints and saying, hey, do these represent a safe program? And of course, the key constraint here is that one I mentioned, forecasted before, that says the type parameter r needs to be a subtype of this union of these two unknowns. And with categorized subtyping, we can break this down into two steps. First, we say, okay, well, the categories of R need to be a subset of the categories of this union. And we can see from this explicit constraint that R belongs to the categories any or error, and those are covered by our union. So we're good there. The second step is I need to break down how we reason about R into these two separate categories. So I'm going to say, okay, and for one case of the union, I know it belongs to the category any. So I can use this notion of categorized subtyping that says, okay, R needs to be a subtype of V when restricted to category any. In the other case, I can say, okay, R needs to be a subtype of E when restricted to category error. So these categories sort of are like filters that I'm imposing on these flows in my program. And then I can walk through these flows and say, okay, for this filtered flow, is this safe? So here I have R flowing into any, but in general, that would be problematic. However, because I've restricted to this, or I've applied this filter that says we only care about any, it becomes trivial, right? Because anything that belongs to category any is already going to be a subtype of any. And we can do that with error and through the rest of the constraints and find that they're in fact a consistent constraint set. But once again, what we haven't figured out is what actually are V and E in this, right? We just constrained them, we haven't defined them. And it turns out that there's, again, one unique answer for this, which is that V needs to be the intersection type R with any, and E needs to be the intersection type R with error. And that's weird because we didn't have intersection types originally, but now all of a sudden I have these intersections, which illustrates that inference ends up requiring intersection with categories in order to be able to set programs using handle, for example. And that's problematic because intersections, being dual to unions, need the similar restrictions as union in order to avoid exponential blowup. And since we need to be able to intersect with arbitrary categories, that consequently limits what categories can be. And so if you saw Michael's talk on rich errors, he mentions, okay, errors can't be generic in the prototype that we're using for experimentation, and that's because of this issue with inference that came up. But now that we've recently discovered outference, we realize we don't need these V and E solutions anymore. We can get rid of these intersections with categories and just drop those restrictions on categories in general. And we figured out that that means that categories really can just be arbitrary class or error names, even if they're generic. And since classes are included in this, we were surprised to discover that means that we're going to support unions that we really hadn't intended for, like integer or union string. Which gets me to a really important disclaimer I should say at this point, which is, yes, we can do this, but should we do this? And that's not what this talk's about. So disclaimer for the rest of the talk is that this outference discovery is really recent, and this is me sort of brainstorming with what can I do with this now that we've realized I'm no longer bound by these impositions that inference was imposing. So recognize that the rest of this talk, the ideas in here are half-baked. These aren't tested or approved by the team. This is me having fun in the weird ways that I have fun with this new tool that I've made. And I'm just exploring what it is I can do now that I have this tool without worrying about what I should do. I'll save that for another day. But that said, I'm presenting this partly because I'm interested in your thoughts on these new possibilities. So do collect those thoughts and come share them with me after the talk. So with that in mind, I want to share this cool idea, well, what I think cool idea is, that I came up with when exploring these possibilities, which is local objects. So to give some context, let's suppose we have some typical line reader interface that reads a line from some input and returns a string or null when there's no more input to be read. Right, I can print all the lines of some interface by just saying while true and then print until eventually a null gets returned and return. But I'm going to introduce this new little annotation, which says that this input is being used locally. And that is something that this algorithm, I'll go into how later on, will enforce by saying, hey, this reference is not allowed to escape this function call. I'll use your line reader, and then once I'm done, once my function returns, I do not have it anymore. And that's useful for me to make sure that this line reader isn't accidentally escaping into my internal data. It's useful for you to know that I'm done with it, and you can do whatever else you want with it after you've made your call. So that restriction itself has some possibilities. But being the algorithmic type theorist I am, I wanted to explore about what kind of new things can I do once I have this restriction in place. And so I started exploring this idea of, well, what about asynchronous reading, right? So suppose I want an asynchronous version of printing lines, right? And I'm given this read function that suspends every time I call it. What can I do with that? Well, I'm going to make a local object that implements line reader. And here, local means that this object is not allowed to escape from this function call. So again, the type checker will make sure that by the end of this function, this object is done. And you might notice that this object does something weird, in that it uses the suspending read function inside its implementation of readline, but readline does not suspend. And the reason why I can do that is because this object is local. And so I know this method will only ever be run within the context of this function. And so I can make this outer function suspend whenever I need to. And more generally, these local objects are allowed to use local control safely, right? So they can break, continue, so on. They're sort of a generalization of this pattern we see with calls in place. And with that, I can hand this off to print lines. And of course, that means, OK, well, now I'm giving readers somebody else. That could be a problem. But because I've already declared that print lines keeps its object local itself, I know that that object still won't escape the lifetime of this function. And so this is perfectly safe code. I can guarantee that things will only suspend when they're allowed to suspend. And so what I notice is I'm basically adapting this asynchronous input to some code expecting synchronous inputs. And maybe I can play with that and scale this up a little bit more to look at this sort of asynchronous versus synchronous I/O problem that we all are familiar with. So again, set some context. In this setting, in this typical synchronous setting, you'll have some interface. I've called it chunk reader. That's the low-level access to how do you interact with some inputs. Right? It reads chunks of data at a time. And then, because this is a pain in the butt to work with, we generally have some class like buffered reader that takes this low-level interface and adapts it to my high-level line reader interface. And then the platform provides me forms of input, such as a synchronous file reader that takes the name of the file and then implements chunk reader to read that file from the operating system. And we can chain these all together in a way that we're all familiar with, right? Where I set my file reader, I give it to a buffer reader, and then I give that to print lines. And we can do this all with asynchronously too, right? And it looks exactly the same, except we've suspend everywhere. And that's frustrating because we basically duplicated our code, and many of us have settings where we'd like this code to be able to work on multiple platforms, some of which are synchronous and some of which are asynchronous. And we get all this duplication because these two platforms can't agree on how files should work, right? So with that observation I made in the last slide, I said, OK, well, is there some way I can use local objects to consolidate this code? And so I'm going to first do the step-by-step by getting rid of async chunk reader. And what I'm going to do is introduce this notion of a suspend class. I'm going to say async file reader is now a suspend class. What does that mean? Well, it's kind of an adaptation of that idea, that object I created in my previous file that had to live inside this suspending function. So a suspend class is one whose instances can only be created from within suspending functions, and who are not allowed to escape that suspending function. And as a consequence of that restriction, that means that all its methods are allowed to suspend arbitrarily, even if they're not suspending methods, because they can suspend essentially the whole class. Which makes it possible for this asynchronous file reader to implement this chunk reader interface, even though it's essentially the synchronous interface that we had designed. Of course, that also means we have this restriction with how we use it down below that says, hey, now you have to make sure you keep this thing local to this print lines of async file function. Which is a problem because the first thing I do then is I hand it off to async buffered reader. So let's visit async buffered reader and get rid of it. And say, okay, well, buffered reader has this nice thing where, yes, it's going to use its input every time it needs to read some lines, stuff like that, but never really exposes that input. It doesn't give it to anybody else, right? It just interacts with it and wraps it. So essentially, we can say, okay, what it's doing is it makes sure that input is kept local to the class. That is, the parameter is not allowed to escape the object itself. It's just internally referenced. Which means now that our buffered reader down below actually has the ability to keep that input local to itself, provided that it's also kept locally. But of course, the only thing we do with it is a handoff to print lines, which we've already established does keep its input local. And so we can chain these all together, and this chaining is perfectly safe. And we can recognize that with a type checker. But now, and the nice thing is we have basically the same code still on the left, right? We haven't had to change that at all. It's the same program we had before. But of course, we still have 2 copies of this bottom code. We've consolidated our standard library, but now all the users of the standard library still have 2 copies. Is there a way we can get rid of that? So what I can do is say, okay, I'm going to replace these with a single function, print lines of file. And instead of having this function directly construct sync file reader or directly call async file reader, I'm going to have it call io.filereader. And what's io? Well, it's a context parameter. That's in the io environment that returns the file reader appropriate to the current io environment. And because I can make using this entirely locally, I can call it local, and now I can call that within any setting with either an asynchronous or a synchronous implementation of io environments. And so I can consolidate that code as well using local objects. Now, this is all me brainstorming about what I can do with outference, but I haven't really talked about outference anywhere in this, right? This is just local objects. So why am I talking about this? Well, I have to, anytime I want to add a feature to the language, especially because I particularly want this language to be decidable, I have to have an algorithm that supports that feature. So I need some algorithm for reasoning about all this locality, and that's where outference comes into play. So the way I can support this all in a decidable manner is by outferring lifetimes in my program. The idea is that this local is, keyword is a modifier of function parameters and objects, and I can take that modifier and use it to translate these functions and objects into using a form of lifetime polymorphism. If you're familiar with REST, you'll have heard this notion of lifetimes. And my program then has all these flows, and those flows establish constraints between these lifetimes, and my outference algorithm can then check that those constraints are all consistent, and making the program safe. And because outference is decidable, complete, it does this in a reliable manner. That means we can completely hide these lifetimes from you. There's no reason for me to expose it to you. Right? If I don't have to have, just like I don't need to have a name for forever, I don't have to have names of all these intermediate lifetime types to expose to you because you never see that. It's just entirely hidden behind the scenes. Whereas with inference eventually is going to expose these types, especially if it's incomplete. Right? At some point, you'll get some error message with, hey, this lifetime is incompatible with that lifetime, and then you have to manually specify your lifetimes, and you end up getting code like this, where lifetimes get threaded throughout your program. And all of a sudden, this feature just becomes intractable, right? This is just too complicated to not really interfere with how we're used to working with Kotlin. But because outference hides all this, I just have these few keywords. It looks very similar to what we're used to. And outference, as sort of more generally, kind of addresses this complexity barrier, right? This problem that we want to add advanced features for y'all, but we don't want to make your experience too complicated either. Which is great, but in trying to expand what Kotlin can do, I've run into yet another problem that I'm facing, which we need to talk about. And that problem is with any question mark, and more generally with the assumption that everything is an any question mark. And the reason why this is a problem is, well, turns out not everything is an any question mark. Right, so errors aren't any question mark, right? Because the whole point of errors is that they're a new category that is disjoint from this any question mark category, so we can do these unions efficiently with them. These local limited lifetime values, right, also aren't any question marks, because any question marks can be put arbitrarily onto the heap. And the whole point of these is that they are restricted and kept local to that stack frame. And other features I've been exploring the applications of outference for, like better support for unboxed value classes in the presence of generics, is going to be compatible with any question mark, because the whole point of them is that we don't make references, and so then clearly not going to be any's. And what I just kept running into when exploring these new possibilities of outference is that this assumption that type parameters are always any question marks is really limiting what Kotlin can become. And obviously this assumption stems from Kotlin's days of originally being a JVM language, where everything is an any question mark. And it's still super important that we keep that interoperability, but we can provide that same interoperability without making this assumption about all our types. So I wanted to dig into what other aspects of Kotlin really rely on this assumption. How else has this implicit assumption baked into the Kotlin language design? And the key answer that I found is that equality in Kotlin uses any question mark, right? We have this equals method on any that takes an any question mark. So clearly this is assuming that everything is an any question mark. And this effectively means that equality is entirely dynamically typed, right? And if you look at the implementations of equality, they tend to be not entirely safe and not entirely efficient. And I just don't view this as a particularly compelling argument for why everything should be any question marks. So I thought, well, maybe we can do better, right? We have this new tool that I've developed. Maybe I can use this tool to solve this problem in a way that we all would benefit from. So I started exploring how to provide type-safe equality in Kotlin using outference, along with comparison arithmetic, other kinds of things in this pattern. And the first thing I did is well, let's visit how we can manually provide type-safe equality, right? It's actually possible for us to do this ourselves. There's a good reason why we don't, which I'll get to in a bit, but we can actually do this all ourselves if we wanted. Right, so I could write an interface equatable that shows me how to equate two t-values. And I could write an extension method for iterable that just contains, where I give it an equatable and then it looks for a matching value using that notion of equality. I handled it. And I could also write an object that shows how to implement equatable for strings and so on. And then I can put all these pieces together to be able to check that a given list of strings contains a given string, right? But what we know from plenty of experience is that this very quickly becomes tedious and cluttered. This simply does not scale to a feature that is used so widely in our code bases. But maybe we can use this as some sort of inspiration, and we can incorporate this with some ideas from other languages and some research I have in this space from a long time ago now, 10 years ago, and incorporate this notion of shapes and constraints that I developed when exploring decidable features for Java, or extensions to Java. And in this, we're going to take that same code, but just fiddle with a bit to remove that inconvenience. So I'm going to have that same interface, but now I'm going to add this annotation that says it's a shape. And what that means conceptually is meant to describe the shape of the type T in this case, some structures it must have. And what the effect of this is that it says, OK, now I'm going to add to the global scope this equal method. And it doesn't require a receiver anymore, unlike what we had before. It just says that you can only call this when you know that T is equatable. So we've moved this explicit receiver to being implicit constraints on the type. And then when I want to write iterable contains, I no longer have to explicitly pass an equatable. I add this constraint that equatable, and I also don't need an explicit receiver when I call equals. I just say equal, or I could use an operator, right, if I had operator overloading, and the constraint there will sort of take care of that receiver for me. And I can take that same object I'd implemented before, right, for strings, and now I'm going to call it, for funsies, a shapeshifter. And the idea is that it shows me how strings that has this shape for equatable. And because I've labeled it like this, what the type checker will do is say, OK, well, I see this as an equatable of string specifically. So next time I need to know that string is equatable, I'll use this object in order to satisfy that constraint. So that now when I call list of with contain, or call contains, I no longer have to pass it anything. Instead, the outference algorithm will automatically synthesize that the notion of equality you use here is string equator. And it'll take care of all that stuff we did manually automatically for you instead. And the way it does this is actually very similar to how we saw handled in method resolution. It says, OK, contains has some unknown T, and this T needs to be equatable. I'm going to listen to this T, and once a lower bound comes along, like string, I'll say, OK, well, there's a shapeshifter that works for strings, and that's the one I'll use. And other things we can do is make sure there's only one shapeshifter so we don't have ambiguities and so on in our program. And so it'll work basically the same way that we have currently with with static typing rather than dynamic typing. And this, again, lets us address this problem that we had with any question mark, which was getting in our way, and now really expands what we can do with the Kotlin language. So what I've been finding is that this sort of oddity of the algorithm that at first I spent a lot of time figuring out how to solve actually turns out to not be a problem. It turns out that it just enables a lot of new things that we didn't know were even possible before. And this is all very new, so we're still figuring out what of these possibilities are actually directions we want to go. And I'm hoping y'all will help me with that process. So I do actually have a few minutes of time for questions, although I guess maybe not because I had to go late because of lunch or because of the technical error. But please, if any of this interested you, or if you had any concerns about any of this, or if your own features are like, oh, maybe this is possible now, come find me at the booth over there. I would love to share and discuss and brainstorm with you all as well. And thank you very much for coming to my talk. I'll open up to a few questions, and don't forget to vote.